Hey everyone, ready for your last organic chemistry lecture? Goodness knows I am. Reminder, the material in this video is not going to be on our exam number 4, but it is fair game for the final exam. I'm just getting a little bit ahead so that I can focus on other things like writing and administering and grading exams and all that fun stuff. Good, so our last chapter is also our last biochem chapter. One really important class of biomolecules that we haven't covered yet is proteins, polypeptides, and the amino acids that make them up. As usual in our discussion of biomolecules of all sorts, we are not going to focus on biological function here. That's a topic that belongs in your biology and biochem classes, especially your upper division classes. So that means what that means for you practically is a goodly part of this chapter is going to get cut. You won't be responsible for it. So see the class notes. I tried to be clear in the class notes, and I double-checked, and the class notes are also consistent with the syllabus. We are instead going to focus on the very same things in this chapter that we've always focused on all semester, mostly structure and reactivity, so that we can understand the structure of both individual amino acid molecules and the polypeptides or proteins that they make up, and also understand somewhat about their reactivity. So that's going to be my goal here. It turns out that there are 20 amino acids that are found in nature, in proteins, in living creatures. They all have a structure something like this, but we want to be a little bit careful about this. This is something that I could wish your book were a little bit clearer on. We call them alpha amino acids because the amino group and the carboxylic acid functional group are on the same carbon. And so the carboxylic acid is right next to the carbon that bears the amino group. And so that's all that alpha really means. It's just a way of saying next to. So the two functional groups are right next to each other. And this so-called side chain R has 20 different possibilities. And you can see it already in our class notes, but I might as well cut to the chase so no one panics. You do not, repeat, not have to memorize all 20 amino acids. If you go on to some kind of biochemistry course, you might very well have that pleasure, but not for this class. Well, I'll tell you what. What if you memorized one? We can do one, right? How about memorizing the easiest one? The easiest one to memorize is just where R, the side chain, is hydrogen, right? And so that's the only achiral amino acid. But that one's easy enough to memorize, I think. So it's okay, go ahead and memorize maybe that one, that's fine. The other 19, don't worry about. If you need to know them, I will give you whatever information you might need. And I have some examples later on in this video as well. Now, this structure here is missing a couple of things. First of all, it's not being clear about the stereochemistry. And the stereochemistry of these chiral carbons is known, but I just want to avoid burdening you guys with that. But I do want to let you guys know that that stereochemistry is known and always the same for all of the amino acids. One rather annoying byproduct of all this, I guess, is you might remember that when we recently talked about sugars, we said that in these monosaccharides, all of the natural sugars are in the D form, and the sugars that are in the L form are unnatural. In other words, they don't occur in living systems. They need to be synthesized in a lab. Unfortunately, for reasons I don't know, maybe it's just a coincidence. Unfortunately, though, it's the exact opposite for amino acids. For amino acids, it is the L amino acids that are natural and the D amino acids that are unnatural. Like I said, I'm not really concerned at this point as to whether you're able to draw these with the correct stereochemistry. I just want to point out that we could if we wanted to. All of that information is known. That's one thing that this structure doesn't make entirely clear, other than not mentioning specifically the side chain R. The other one is that this structure is actually, in terms of what we encounter in everyday life, It's a little misleading. This is the structure that the molecules take in the gas phase. So in other words, if you do whatever it takes to essentially evaporate or maybe sublimate is a better word, and get this material into the gas phase, this is the form that the molecules will take. When do we encounter things in the gas phase? Well, approximately never, right? Except for things that are already our gases, like oxygen or nitrogen, right? So this is not the form that amino acids take in actual living systems. Rather, the pure compound, so the pure crystalline amino acids, will look like this, or this is also the form that amino acids take in aqueous solution, which is pretty much what living systems are, right? We're mostly water, at pH equals 7. And I just want to let you guys know also another thing. Your book, and also therefore the OWL problems, go on a lot of tangents about, oh, this is pH 8.3, and over at pH 4.7, this happens. I just want you to focus on 3 different pHs, 1, 7, and 14, because those are the easy ones. Those are the ones that are always clear. And I would like you to be aware of how to draw the structure of any amino acid, and even maybe a small polypeptide, say a dipeptide or a tripeptide, at pH 1, at pH 7, or at pH 14. Those are the only 3 pHs I'm interested in, because those are always clear. Those are always unmistakable. So we'll just focus on those. So this is the form that amino acids take in solution at pH 7. This type of structure where the molecule is both a minus charge and a plus charge, first of all, species like that are known as zwitterions, Z-W-I-T-T-E-R-I-O-N, zwitterion. And this is, I think, at least the second time this term that all 3 of you who, like me, took German in high school, or maybe you spoke it at home, you just won the internet yet again, because the term comes from the German word Zwitter, which means twin. So it's a twin ion. It's got both a plus charge and a minus charge in the same molecule. And on the other hand, it's maybe not too surprising that the molecule would take this form. We already know that carboxylic acid functional groups are acidic. We just did a whole chapter on that. And so at pH 7, we are in general well above the pKa of these carboxylic acids. Normal carboxylic acids, isolated from other functional groups and not with an amino group in the same molecule, typically have pKa's round in about 4 or 5, somewhere in there. And as we'll see, for the amino acids, the carboxylic acid functional group is an even lower pH. It's generally round in about 2.5. So at 7, we are well above that pKa. So that carboxylic acid functional group will be deprotonated, and we will have the conjugate base, the carboxylate ion, instead. What about the amino group? Well, we know we did a chapter on amines. I think it might have been chapter 11. Anyway, we did it much earlier in the term. But in that chapter on amines, we pointed out that amines are basic. And so they're not the strongest bases in the world, but they will accept a proton. Certainly an amine would accept a proton from the likes of a carboxylic acid group. And the pKa of most ammonium ions is generally round in about 9 or 10, something like that. And these are no exception, the amino groups in amino acids. And so at a pH of 7, we are now below the pKa of that ammonium ion. And so that's going to be protonated. In other words, the solution is too acidic for this to be the free amine, NH2. Likewise, it's too basic for the carboxylic acid to be the free acid. It's going to exist as its conjugate base. So that's one thing. And again, that's very clear. Now, we do have to bear in mind that some of these side chains, and you'll see that when you look at the table in your book, some of those are ionizable. And so we need to be aware of what, at least roughly, the pKa's of those functional groups are. Most of them are either other carboxylic acid groups or other amino groups. And they're all going to pretty much mimic the carboxylic acid functional groups and the amino functional groups that are on the actual alpha carbon in terms of their pKa's. There are also a couple of others, really, which we've run into already, so we're already familiar with. One of those functional, or one of those side chains rather, has a sulfhydryl group. that would be cysteine in particular. And again, I don't care if you memorize that. But the side chain R on cysteine is CH2SH. And so we need to remember thiols are quite acidic, quite a bit, well, maybe not carboxylic acid level acidic, but quite a bit more acidic than an alcohol. And what we'll find is that an alkaline pH of 14, that's more than high enough to deprotonate the sulfur. And so at alkaline pH, that will exist as the thiolate ion, CH2S-, but not at pH 1 or pH 7. There you'll just have your thiol. Another species that's quite a bit more acidic than otherwise meets the eye is phenol functional groups. And you will find one of those in the side chain of the amino acid tyrosine. So tyrosine's another one that is an OH group and a benzene ring. Remember, phenols are special. They are alcohols, but they're at least 1 million times, maybe up to 100 million times more acidic than standard aliphatic alcohols, where the OH is just attached to an alkyl type carbon. And so tyrosine also will be deprotonated on its side chain at pH 14. And this is something that I think you'll get a good deal of practice in the OWL assignment. That will be your last OWL assignment, and as I recall, it might not even be graded. I don't think there were enough questions. But I gave you all the ones that I thought were relevant among the, roughly twice or 3 times as many as they gave me. Most of them I said, I don't want them to bother with this stuff. This is going well beyond what's important for our purposes. Good, so that's at pH 7. What about at pH 1? Well, at pH 1, we're now quite acidic. That's pretty much as acidic as you can get in aqueous solution. Oh, what have I done here? I think I put a lone pair in midair over here. There we go, that's better. So at pH 1, we're not only below the pK of the amino group, so it stays protonated, it becomes the conjugate acid, but we're also below even the pK of the carboxylic acid functional group, which is going to be at about 2.5. So at 1, we're below that. So both of those will be protonated. And again, you'll also need to consider the R groups. Well, like I said, we'll do some examples of that later. What about pH 14? Well, at pH 14, I think I maybe meant to put the lone pair here. At pH 14, now we're above the pKa of both of those functional groups. So not only is the carboxylic acid deprotonated, and we have the carboxylate ion, even the amine gets to stay in the free amino form. It's not the ammonium ion, because at pH 14, we're above the pKa of the ammonium ion, which again, you'll recall is a pK of generally 9, 9.5, 10, somewhere in there. So at 14, we're above that. And so these are important distinctions to be able to make, even without considering the stereochemistry. Good, so that gets us through most of this stuff. I want to just mention the idea of the isoelectric point. This is something that if you take biochemistry, they're probably going to make a big deal about. I don't want to make such a big deal about it, but I want to at least give you enough background so that when you get to that point, when you start talking about, let's say, electrophoresis, which we're not going to do here. It's in your book, but you're not going to be responsible for that. But it's going to be important to be able to understand isoelectric point. And it's really not a complicated concept. As I point out here in the class notes, where I define the isoelectric point, it's abbreviated as PI. It does not have to be an amino acid. It doesn't have to be a biochem thing in particular. You can consider the PI of any ionizable species. And it's defined as the pH at which the overall charge on all of the molecules in the sample is 0. And that's quite easy to calculate for any amino acid in which R is non-ionizable, one that's going to have the same form at all 3 pHs, 1, 7, and 14. So maybe it could have just an alkyl group like alanine or valine. Maybe it could have just an alcohol functional group like serine or threonine, right? Those are going to be all the same at pH 1, 7, and 14. So those are non-ionizable side chains. In those cases, it's very simple to calculate the isoelectric point, assuming that you're given the pKa values of the carboxylic acid functional group and the ammonium ion on that species. They're all around the same, but once you're given those 2 values, all you do is average them. That's it. You just add them up and divide by 2. And just so you're aware, since most of these carboxylic acid functional groups of pKa's round in about 2.5, and these ammonium ions are all rounded about 9.5, well, we can average that in our head. 2.5 and 9.5 is 12. 12 divided by 2 is 6. So all of the isoelectric points of the amino acids where R is non-ionizable are going to be rounded about 6, pretty close to 6. It is quite a bit more complicated when the side chain R is also ionizable. There's a way of calculating it too. I certainly don't care if you know it for our class. You probably will be going there in any upper level biochem classes that you might take later on. For us, I don't want us to be concerned about it. My only concern here is that I at least mention the term isoelectric point, that you have an idea that it's of what it is and that it's on your radar screen, and that you're aware that at least for when R is non-ionizable, it's dirt simple to calculate. You would be given the 2 pKa's of these two groups, and you would just average them. Just add them up and divide by 2. That's it. Good. So that's, I think, all we need to say about that. What about reactions of amino acids? Well, we're at the end of the term. We already know all that we're going to know about carboxylic acid functional groups. We just covered them in our previous chapter. And likewise, we already know a lot about amines and how they behave. We know that they're basic. We know that they can be nucleophilic, and they can undergo certain reactions that other nucleophiles can also undergo. In chapter 10, for example, which is not that long ago, we said that you can esterify carboxylic acid functional groups by a Fischer esterification reaction. So I've given you the reference if you need to review that. That's simply done by acidifying the material and heating it up in some alcohol. Generally, the alcohol is pretty small. It's almost always methanol or ethanol, or at least something not much bigger than that. And in the end, you will esterify the carboxylic acid. Notice also the amino group, at least at pH 7 or near pH 7, is going to go back to the free amine. At least we will certainly treat the compound so that we can isolate a neutral product. We'll get it to whatever pH we need to in order to let that happen, because we want to be able to isolate a neutral compound. That's always our goal. So, and that's just one example of these reactions. You could do any of the other reactions that we talked about on carboxylic acids in the previous chapter, and this carboxylic acid functional group will do the exact same thing. For instance, you could treat this compound with LAH, lithium aluminum hydride, and it would unquestionably reduce the carboxylic acid functional group to CH2OH, and you would leave the amine alone, of course. It doesn't do anything to amines. I'm here using phenylalanine just as an example of an amino acid. I could have picked any of them. But assuming there's not also another carboxylic acid functional group here, which there would be if your amino acid were aspartic acid or glutamic acid, in which case you would simply esterify that as well. You'd esterify both carboxylic acids. But short of that, whatever the side chain is just along for the ride. What about this amino group? We've learned a number of things that you can do with amines. Maybe rather fewer, since amines are not as reactive as a lot of other functional groups. One thing we said is that you can convert an amine to an amide by treating with now one of our most reactive acyl derivatives, as we discussed at the end of chapter 10. So I'm here using benzoyl chloride as an example, but you could use any acid chloride or any acid anhydride. And the result will be whatever this acyl group here gets transferred onto that nitrogen. And so you wind up with an amide. In this case, you'll get the benzamide of this functional group. And so reactions like this are quite common and fairly straightforward to carry out. Once again, of course, we'll isolate a neutral molecule. So be careful that everything's obeying the octet rule and is a formal charge of 0, and that's what you will isolate. Good. Well, what happens when you start sticking these guys together and making polypeptides? I'm pointing out here what's sort of the essential things to know for this case, just to be aware of what the structure of small polypeptides is, because my belief is if you understand that, then in principle you understand the structure of big proteins. If you understand how to put together 2 or 3 amino acids, well, in principle you understand how to put together 500 amino acids, or 3,000 or 30,000 amino acids. The same thing, just happens a lot more times. Good. So I've laid all that out here. And again, we already talked about amides and how they're formed, how it is that you can form an amide with the right set of reagents, and either an amine and an amine and a carboxylic acid, and so they come together and form the amide. Or you could convert the carboxylic acid to an acid chloride, let's say. Those are details from chapter 10, but the idea is that if you bring together an amine and a carboxylic acid, the product should be an amide with in principle loss of a water molecule. So a couple other things to be aware of. When we draw polypeptides, and really I would suggest it too for drawing individual amino acids, by convention we put the amino terminal, or the free ammonium group, at the left, and we work our way to the carboxylate terminal, the carboxylate group. We put that at the right. Like I said, OWL will drive you insane with a pH 10.2. Don't even worry about it. Like I said, I only want you to care about 3 pHs, 1, 7, and 14. Those are clear. Those are the easy ones. I'm not really concerned about 11.8 or whatever. Those are the easy ones, because those are always clear. It's always unambiguous what all of the ionization states are. Good. So I don't know that I would ask it exactly like this in the exam. I guess I would have to change it up somewhat, wouldn't I? Because it would be multiple choice. But be that as it may, this is good practice for the exam and for OWL. So draw serine and glutamic acid at pH 7. You would either be given a table or you would be told what the side chains are. Then draw the dipeptide serine glutamic acid. And I'm saying here at pH 7. We'll start at that one. That's the easiest. So, well, serine would look like this. All I've done is I've replaced R with the side chain I'm given, CH2OH. And likewise for glutamic acid, CH2CH2CO2-. And so at a pH of 7, the ammonium group will be protonated because we're below the pK of the ammonium ion. And of course, the carboxylic acid functional group will be deprotonated because at pH 7, we're too alkaline for that proton to stay on. So that will be true for both of them. So that's what the individual amino acids would look like. And then, in order to bring them together and make the dipeptide, what you need to know is that when we bring together this carboxylic acid carbon and that amino nitrogen, we're going to form an amide. And another thing that your book actually points out in chapter 10 to its credit is remember that this part of the molecule, the oxygen, the carbon, and the nitrogen here, that's planar. Right, because there's a little bit of double bond character between the carbon and the nitrogen. You can draw another resonance form. That would be a good exercise, where you have a minus charge on oxygen and a plus charge on nitrogen, and a double bond between carbon and nitrogen. So there's a significant amount of that contributing to the overall structure of the molecule. That means that that portion of the molecule, and it's also true for any amide functional group, doesn't have to be in a polypeptide. But it means that this portion of the molecule, wherever you have an amide linkage, or also called a peptide bond, they're one and the same thing, that part of the molecule is going to be flat. And that restricts the possibilities for the shapes that the molecule can take. That's what leads to why proteins have the shape that they do. And that in turn leads to why proteins have the function that they do. So again, we're not really talking about biological function here. But I would like to at least drop it in the back of your mind that, oh yeah, this part of the molecule is planar wherever that amide bond occurs, and so that's going to limit the possibilities in terms of our overall structure. But anyway, in order to form the dipeptide, that's all you do. You attach this carbonyl carbon to that nitrogen, and you make an amide. Period, full stop, that's it. And so that's how that would look, that dipeptide would look at pH 7. Again, we're not concerned with stereochemistry here. Just these flat structures is fine with me. And if you wanted to take another amino acid, well, you would take the carboxylate terminal and attach it to the amino nitrogen of the next one. Or you could take this amino nitrogen, attach it to the carboxylic acid carbonyl carbon of another one, and extend it in the other direction. That's essentially the idea. And of course, there are enzymes that do this for us. That it doesn't exactly work to just sort of throw these things in the flask and pray they come together correctly. That's not going to work. And I don't want to go on too much of a tangent, but you might want to think about it. What if you threw these two things into some flask, maybe with an acid catalyst? Would you get this compound? And it's almost a trick question. The answer is yes, you would get some of it, but you would also get the reverse, where the glutamic acid's on the other side. You would get two of these stuck together, two of these stuck together, three of these stuck together. You get a big mess is what you'd get. So that's why it's important to understand that the order of these things really matters. And I'll leave the rest for your biochem class. I don't want to focus too much on all that. But I just want to put these ideas, I just want to give you a taste of these ideas so that you have that background when you go on and look at the biological function in more detail. And I even gave you a little problem to work out. What would all of these three molecules look like at pH 1? What would they look like at pH 14? So you might want to go over some of our information over here. Last but not least, we learned a little bit about thiols in chapter 17, right? Thiols are the, wait a minute. That's not 17. That's chapter 7, right? That's our alcohols chapter. Yeah, there we go. So please make that change in your class notes. I don't know why I had 7. Wait, I just did it again. How about in chapter 7? There we go. Change it to that, because that was our alcohols and thiols chapter. Thiols are just the sulfur derivative of alcohols. And so thiols can be oxidized to disulfides. I think we might have mentioned it. It's a long time ago. I don't quite remember. But just in general, regardless of what R might be, you can take two thiol molecules and they will undergo an oxidation reaction. There are, again, biological oxidizing agents like NAD+ and FAD that will do this for us. And essentially, these two molecules come together and lose a molecule of H2 to form the corresponding disulfide. And the opposite reaction is also possible. You can break the disulfide bond and reduce it back to two thiol functional groups. Where this matters for us is, again, one of the amino acids, cysteine, has a thiol side chain. The side chain is CH2SH. So you can bring together one sulfhydryl group over here, another one over here, and oxidize them and bring them together and make the disulfide. And of course, again, it's almost like magic. There's enzymes that take care of all this for us. That will also limit the possibilities of the structure of the protein. And these two amino acids could be very far apart in what they call the primary structure of the protein. They might be 500 or 1,000 or 5,000 amino acid residues apart. But there's, the thing can fold and bring these two together and make a disulfide linkage. And disulfide linkages, hydrogen bonding, ion dipole type forces, those all affect the structure of proteins very profoundly. One practical application of all of this breaking and forming of disulfide linkages is if you've ever gotten your hair permed or know someone who has, or I don't know if people still do that. I had a colleague at my previous school, a man actually, at this big perm all the time, looked kind of like Bob Ross, but that's another story. Interestingly, he was in the art department. I never put that together while I was there. Be that as it may, of course, in my case, I just wish I had enough hair that I could get a perm if I wanted to. But in any case, those of you who ever had your hair permed, it's this chemistry that's going on. First, what they do is they treat your hair with some reducing agent that will selectively cleave all of the disulfide linkages in the proteins in your hair. And then they put in all those things, or whatever it is they do. They get everything into the shape they want it. And then they add something that reforms the disulfides. And so now your hair will be kept in that shape. So it's basically this exact chemistry that's occurring there. So that, I think, is a good place for us to end. Again, a reminder, this material in chapter 17 will not be on the 4th hour exam, but it is fair game for the final exam. The final exam will be cumulative for the whole term, and I believe I've already put up topic lists for both chapter 4 and the final exam. So other than that, it's been a pleasure. I wish we could have done this more in person, but it is what it is. And I, of course, will still be available for office hours for the rest of the term. So other than that, have a good day.